Hi everyone, welcome to lecture 13 of neural computation, synapses and compartment models. Today we're going to take a more detailed look at models of neurons, building upon our increasing level of biological fidelity that we met with the Hodgkin-Huxley model. And this time we're going to look at multi-compartment models, which will help us model how changes in the membrane potential due to currents being injected by neurons, other neurons, how that change in potential will propagate across the physical extent of the neuron. To date, we've just been modeling neurons as point masses, and we want to expand that out to be more realistic. We're also going to look at conductance synapses, which is to say models of synapses that treat the transmission during an action potential as like a conductance, like we've previously seen in the Hodgkin-Huxley model. The reading for this lecture are Gerstner 3.2, 3.4, Diane and Abbott 6.3 up until the RAL model, and then Gerstner 3.1 for the conductance synapses, and then Diane and Abbott covers that in 5.8 up until equation 5.38. So far, we've discussed how action potentials are produced in neurons through the action of sodium and potassium ion channels in the Hodgkin-Huxley model. But we haven't put much thought into about what happens with the action potential after they are produced and how they inject current into another neuron. And while we have talked about what happens after current is injected into the neuron, this would be our model of how neurons create action potentials. Our models have been limited to point models, neurons that have no physical extent. Today, we're going to develop our model to a higher level of fidelity by building a synapse model that models how effective a transmission from a presynaptic to a postsynaptic neuron is after an action potential, like conductance, as we model the conductance in the Hodgkin-Huxley model. And here we will account for the interaction of neurotransmitters, and we will add these. We will explicitly model an effect of neurotransmitter on the conductance of the synapse, just like we modeled the conductance, the voltage-controlled conductance of the ions in the Hodgkin-Huxley model. And then we are going to extend the model again to have spatial extent. And by that I mean we are going to model the physical dimensions of the neuron, how changes in membrane potential propagate along those physical dimensions. And this will help us build up things like models of dendrites. This discussion will be broken up into two videos. This video is about conductance models of synapses, and the second is going to be about the compartment model of neurons. Now we're going to discuss conductance models of synapses. Here we will be modeling how effective a synapse is at transmitting information with an action potential through the membrane of the neuron, like we did previously with the Hodgkin-Huxley model. However, there we only modeled, with the Hodgkin-Huxley model, we exclusively modeled a postsynaptic neuron, and we just assumed that somehow current was being injected. Today we're going to model the role that the presynaptic neuron as well as the postsynaptic neuron in the effect of transmitting an action potential from one neuron to the other. And we're going to look at how this interaction is conducted through the effect of neurotransmitters on ion channels. The diagram that we are seeing here shows the development of a presynaptic neuron, or the development of a synapse once a presynaptic neuron, this top neuron here, and emits an action potential. What happens within the presynaptic neuron, what happens in the postsynaptic neuron, and what's happening in the synaptic cleft in between the two neurons. And going from left to right, this diagram evolves over time. The action potential as we previously discussed, is a sudden, sharp depolarization in the membrane potential that travels from the neuron body along the axon until it reaches the axon terminal, the endpoint, where it forms a synapse with another neuron. And that's what this is here. This is the synapse. Once that change in membrane voltage reaches the end of the axon, it causes ion channels that control the concentration of calcium ions, the Ca2 plus ions, in the body of the neuron to open. It causes these channels to open. So opening the ion channels allows calcium to enter the neuron, attempting to achieve the reversal potential for calcium, as we saw with the other ions in the neuron body. And this increased concentration of calcium inside the presynaptic neuron causes vesicles of neurotransmitter to migrate towards the cell wall. And that's what these circles here with the blue dots are. These are the vesicles. And what they are packets of neurotransmitter that will, with some probability, fuse to the cell wall. And we see the action, the vesicle fusing here. And through fusing, release neurotransmitter into the synaptic cleft. So we have step one. The action potential has the membrane depolarization has reached the end of the axon. That has caused the calcium ion channels to open with an influx, allowing an influx of calcium. That influx of calcium causes the neurotransmitter to the vesicles to approach the cell wall and release the neurotransmitter into the synaptic cleft, which is the space between the pre and the postsynaptic neuron. Now, through diffusion processes, these neurotransmitters will work their way across the cleft. This is a Brownian motion process. These things will randomly wander around in the cleft until they reach the other side. And once they reach the other side of the neuron, with some probability, the neurotransmitter will bind on a receptor that exists on the postsynaptic neuron, and specifically it exists on the ion channels in the postsynaptic neuron membrane. This binding of the neurotransmitter can cause, for example, sodium ion channels to become open, which will allow for an influx of sodium, which will cause the action potential which we modeled in the Hodgkin-Huxley model previously. Now, there are different kinds of receptors that exist on neurons, and depending on the type of receptor, they will have longer and shorter term effects on the postsynaptic cell. But in either case, we should note that the effect remains the same, that we change the state of the ion channels, that changes the membrane potential of the neuron, which can then in turn change the state of voltage-gated ion channels in the neuron. And if the neuron is sufficiently depolarized, that will induce an action potential in the postsynaptic neuron. So when these neurotransmitter activated channels, more accurately called ligand-gated ion channels or ionotropic receptors, are activated, they permit ions to flow in or out of the postsynaptic neuron, changing the membrane potential, and depending on its current state, possibly initiating the action potential in the downstream neuron. So let's look a little more closely at the ion channels that are controlled by neurotransmitters. There's at least two kinds that we're going to discuss today. The first is the ionotropic receptor, and this is where a neurotransmitter receptor directly controls an ion channel. So when the neurotransmitter binds to the receptor, it causes the ion channel to change its shape, which changes the state of the gating subunits, like we discussed in the Hodgkin-Huxley model, and it causes the ion channel to become active. An alternative setup is what's called a metabotropic receptor. And in this case, the neurotransmitter binds with the receptor on the postsynaptic neuron, but this isn't directly connected to an ion channel. Instead, what happens is that it is binding to a receptor that causes a cascade of activity in the cell, in the neuron, that causes the release of what are called G proteins. And these are also called second stage messengers. The first messenger, or first stage messenger, is the neurotransmitter itself, so 1, 2. And then these G proteins affect the behavior of an enzyme in the cell, which releases another releases another molecule that causes the ion channel to become open or closed. Now, these second messengers can also have other effects within the neuron. So it's not necessarily just opening and closing the ion channels with the metabotropic receptors. And then dopamine, serotonin, norepinephrine, and acetylcholine can bind to metabotropic receptors. Anyway, eventually, these neurotransmitters that are bound to a receptor on the postsynaptic neuron will unbind from that cell, and then they will be returning the receptors on the postsynaptic side to their original state, and then the neurotransmitter will again start diffusing through the synaptic cleft. And eventually the neurotransmitter will be removed. It'll either be removed by diffusion out of the cleft, just literally moving out of the space between the pre and postsynaptic neuron, through enzyme-mediated degradation of the transmitter, or they will be taken up again by the presynaptic neuron, where they'll be recycled into vesicles for future use. And the rates at which binding, unbinding, and removal occur vary from neurotransmitter to neurotransmitter, and then possibly from other factors. AMPA, for example, in the synaptic cleft, binds very quickly to ionotropic receptors, about 1 millisecond it takes to do, and that causes a short burst of sodium influx, which then rapidly unbinds, and that then takes about 5 milliseconds. Whereas if we look at GABA B, that binds very slowly to metabotropic receptors, which slowly opens downstream potassium channels through this this cascade of G proteins and enzymes and other mechanisms inside the cell. And that can take about 25 milliseconds, and then it once again slowly unbinds, sometimes taking more than 100 milliseconds to achieve that process. So now let's look at modeling the synapse with conductances. As with the Hodgkin-Huxley model, we want to describe the current across the synapse by modeling how the conductance of this synapse changes with respect to some state variables. And so again, we're looking at the flow of current, which is dependent on some conductance that can change with time or other state variables. And then it is dependent on the difference between the membrane voltage, membrane potential, and what we're going to call a reversal potential for the synapse. Now, we're not going to get down into the nitty-gritty of modeling exactly every ion channel in the synapse, but because ultimately the activity of this current is dependent on ion channels, it's valid conceptually to think of a reversal potential for a synapse. And then the synaptic channels are less ion selective than the voltage gated channels. So we had a potassium channel, a sodium channel, whereas with the synapses there's a mixture of ion channels in there. And so really the reversal potential that we're going to call E-syn, or synapse, is a mixture of reversal potentials for sodium, potassium, calcium chloride, etc., all the ions in the system. With this abstraction, our model is only going to have two kinds of synapses: excitatory synapses and inhibitory synapses, and we'll denote excitatory synapses by a subscript EXC and inhibitory by INH. The reversal potential for excitatory synapses is about 0 millivolts, while on the other hand, for inhibitory neurons, it's about minus 75 millivolts, i.e., below the resting potential of a standard membrane of minus 65 millivolts. And these reversal potentials are based on various averages of ion permeability, and how this is computed we're not going to get into today, but it is, again, a mixture. It is representing a mixture of ion channels that make up the synapse itself. And this is really this abstraction of the mixture of ion channels, again, is abstracting away some of the complexity of the neuron, which is a modeling choice that we might want to make depending on what we're actually trying to accomplish with our model. Now, for our purposes, this will be sufficient. Now, when we modeled the ion channels, there were one or two state variables that we were concerned about. The activation gate variable and the inactivation gate variable in the case of the sodium channel, and then just the activation gate variable in the case of the potassium channel. For modeling the synapse conductance, there are a few more state variables that we need to concern ourselves with. For example, whether or not the presynaptic cell has successfully released neurotransmitters. That happens with some probability. Whether the transmitter has successfully migrated across the synaptic cleft. Again, it's following a random walk as it diffuses through the cleft. We have to understand whether or not any transmitter that did navigate the synaptic cleft successfully actually bound to a postsynaptic receptor. And then we finally have to ask whether the neurotransmitter then, once it unbound from the postsynaptic neuron, if it diffused or decayed in the cleft. And we should also say that all these statements I've just made are whether or not, but kind of statements. The thing did or did not happen. But in reality, these processes are all probabilistic and they're all dynamic. And this feeds into how we're going to model the conductance of the synapse. We're going to define the conductance, again, because this is the trick, is figuring out how to determine how the conductance changes with time with state variables. We're going to define this conductance as the standard constant conductance, which is then modified by some state variable for the presynaptic neuron, and then some state variable for the postsynaptic neuron. And again, these state variables, like the activation gate channels in the Hodgkin-Huxley model, are unitless and take on values between 0 and 1. And we can also consider them as being modeled like the probability of transmitter release, the probability of transmitter binding. And it will be helpful to think about these two values that take on, or two quantities that take on values between 0 and 1 in this kind of a fashion. However, for now, these are both explicit functions of time, but for now, what we're going to assume is that the presynaptic probability is simply a constant. The probability of transmission is a constant. And we will focus on modeling changes in the conductance as being purely dependent on changes in the postsynaptic neuron. We will come back to visit this later, but for now we're going to start with a constant and then some function of time. So let us look at our model of the postsynaptic conductance. Like with the Hodgkin-Huxley model, we have, again, the unitless quantity between 0 and 1, that's this PS, where S is the particular neurotransmitter that we're modeling. It could be GABA, glutamate, whatever. And then like the Hodgkin-Huxley conductance model, we will use the transition rate formalism, where the forward transition rate is denoted by alpha sub S, and the reverse transition rate is given by beta sub S. The forward transition here is analogous to a neurotransmitter binding to a receptor, while the backward transition represents the process of unbinding, decay, diffusion, etc. However, unlike the Hodgkin-Huxley formalism, we won't specify alpha S and beta S in full biophysical detail. We're just going to have to model the propagation. If we were to do the full biological detail, we would have to model the propagation of the transmitter across the synaptic cleft, which is a Brownian motion. We'd have to keep track of their positions, generate random numbers for them to wander around. We'd have to model the breakdown of the enzyme of the transmitters across the synaptic, the breakdown of the transmitters by enzymes as they cross the synaptic cleft. We would have to require exceedingly small time steps to model this with high fidelity. And this is starting to get to a degree of complexity of the simulation or the model where it's not necessarily useful for our modeling purposes. And further, alpha and beta depend on different biophysical processes They have vastly different time constants. And so what we're going to do is we're going to make a number of simplifying assumptions which hold in almost all cases and make producing an analytic solution much easier. And those assumptions are the following. One, the unbinding rate, beta, is constant, and it doesn't depend on states like voltage, ion concentration, transmitter concentration, just on a fixed regenerative processes like diffusion, degradation, and uptake. Second, we're going to assume that the unbinding rate is slow. This is beta S is slow. Empirical time constants are much larger for unbinding than other processes. Transmitter release, movement across the cleft, and binding. They all happen much faster than unbinding does. And finally, we're going to assume that the binding rate alpha depends on the transmitter concentration near the receptor. And the process of nearby transmitter binding to free receptors is constant and fast. And that is to say, if there is a neurotransmitter in the vicinity of a receptor, the process of that transmitter reaching and binding the receptor is fast. And it happens at a constant rate. So since the binding and the unbinding processes can occur at different rates, we can treat them separately and as one happening after the other. Basically, we're going to say because the binding process is so much faster than the unbinding process, all of the binding is completed before any of the unbinding starts happening. And so we're going to break this up into two windows, one starting from 0, which is the point of neurotransmitter release, from T from 0 up until capital T, which is the end of the binding process. And then the unbinding process happens after T is capital T. So let's tackle the binding phase first. It's here on the left. Again, this occurs from 0 to capital T, and there will be some positive concentration of neurotransmitter existing in the synaptic cleft on the outside of the neuron. And that concentration here is indicated by the square brackets S. Again, S is the neurotransmitter that we're modeling at this point in time. And because the time constant of beta is slow, we can ignore it for the time being. And so we can state that the rate of change of the state variable, the PS with respect to time, is only a function of alpha and 1 minus P of S. So basically, we're saying that while we're binding, the unbinding process doesn't matter, and it only depends on alpha times 1 minus S. And again, this is the propensity to bind times, we could view this as the fraction of channels that aren't bound. Right? Again, it's how inactive it currently is. Not unlike with the ion channels in the Hodgkin-Huxley model. Now for the unbinding phase, here on the right, which occurs at time greater than T, we're assuming that the concentration of the neurotransmitter in the synaptic cleft is exactly 0, that everything that was in there has bound with some receptor, and that means that alpha will be 0 because there's no transmitter to bind, so there's not going to be any countervailing force from the binding process. And then this will then tell us that the dynamics P of S only depends on minus beta S times the state variable. And we can ignore this term after T equals capital T. So now we've got two differential equations that operate over two different windows of time, 0 to capital T and then beyond capital T. And we want to come up with a solution for these equations. And so what we're going to do is we're going to treat the concentration of the neurotransmitter as a square wave that turns on at T equals 0 and then turns off again sharply at T equals capital T, and then that is when the unbinding begins. Now something you might want to consider is whether or not this is a realistic assumption. And so ask yourself, do you think that the release or the decay rate of transmitter concentration matters? And we solve these equations, and this is using the step function over the concentration of the neurotransmitter to get the following solutions. That during the binding period, that is to say from t equals 0 to t equals capital T, the activity of the synapse increases, it asymptotes towards a value of 1, complete activation. And this is in a shape that is controlled by some time constant tau alpha s, and that is simply 1 over alpha s, which is the binding rate. And then after the binding, the unbinding begins. And we see that activity decays away from the maximum value that was attained in the previous time window. So whatever the activity value was, the state activity value was at t equals capital T, it starts and then it decays away exponentially, controlled by a time constant tau beta s, which is just 1 over beta s, which again is a constant, and this one is large. Now, if these equations look familiar to you, they should. They have the similar kind of shape that we developed for the constant current solution to describe how the membrane potential of a neuron changes when we were working with the leaky integrate and fire, the integrate and fire style neurons. So we get this asymptotic sort of charging up, and then once the driving force, in this case the neurotransmitter, is taken away, it decays away exponentially from whatever the maximum attained value was. So let's look at these functions in action. What we see here is a graph of the empirical fit of AMPA for an AMPA receptor, and we see that the current that is injected or that enters a neuron as a function of time. And we see that there are, when we fit the data, we get a tau alpha of 0.9 milliseconds and a tau beta of 5.26 milliseconds. And we also, there is a sort of two phases. Again, this sharp peak here is before the peak. This is the sharp rise in conductance, hence greater current, due to the very small time constant for binding, and then the slow fall off due to the large time constant for binding in the AMPA channel, or the AMPA synapse, we should say. And this is nice because this means our model is capable, it's not perfect. There's a little bit of a gap down here that we'll see when this bar goes away. And there's a little bit of a mismatch here, and we see there are some other, noise, randomness along this line. So it's not a perfect fit, but it is doing a reasonably good job of explaining the data, the biological data we've collected from experimentation. So even if we've, elided some of the biological details, like, what ion channels are in the synapse, we're still managing to get an effective, a model that effectively describes the observations we get in biology. Now, also notice that both the rise and fall portions of the curve is governed by an exponential function. In fact, we can see this for all the different receptors that we've modeled here, AMPA and NMDA, GABA A, GABA B, that there's a rise portion and a fall portion. In this case, it's a fall portion and a rise as it returns back up to resting. But basically, these two portions, the rise and fall, they're governed by an exponential function. So perhaps instead of having two different equations for two different windows of time, what would be really nice if we could just have one equation for time, for all of time. And perhaps this equation might even be visible already on this slide here at the bottom. So we're going to describe this equation as the difference of two exponentials. And so the first exponential is going to give us this sharp rise. And then the second exponential will give us the drop-off, which will be sharp for some neurotransmitters. It'll be like AMPA. It'll be slow for other neurotransmitters like NMDA. And this shape of these curves is controlled by these two time constants, tau rise and tau fall. And they depend on the tau alpha and the tau beta that we had in our previous sort of higher fidelity model of the neuron. But we can also take empirical data and fit these quantities to get the shapes out that we want. So again, it's an abstraction that's useful. We're losing some of the biological fidelity, but not necessarily the usefulness of the model. And so typically the tau rise we see is, it can be somewhere between, 1 and 10 milliseconds kind of order of magnitude, and the tau fall can be somewhere in the range of, low as 5 to as high as 100 milliseconds. Again, orders of magnitude that we're talking about. We also we have to include not only the Pmax. So Pmax is whatever the activation, what is the maximum activation state variable, what value it can take on in whatever time window it takes to exhaust all of the neurotransmitter that is entered into the synapse, into the cleft. But then we also need to include this term B, which is again just another coefficient that ensures that the postsynaptic state activation function at capital time T is equal to Pmax. And so this is just some a little bit of math here to make the numbers, to make the model fit the data. But we can actually simplify this even further. For a very small tau rise, that is to say a really sharp jump up like we see here in AMPA, it's basically just a straight line. And so almost a vertical straight line. And so we can update the postsynaptic neuron state. Instead of by simulating an exponential function, we just add a constant value. We just add Pmax to that the state variable, and then we just let an exponential decay cause the p-value to drop off and return back to whatever the resting state is. And so we can write the rate change of the state variable is equal to, that is to say, the derivative, the time derivative of this thing is equal to 1 over tau fall times the activation function at time t. And that just lets us make this model a little bit simpler. So let's look at some different neurotransmitters. GABA. It has a reversal potential of around 70 to 75 millivolts. It's an inhibitory neurotransmitter. That's why these curves here, GABA A and GABA B, are below the zero line on the synaptic current. And so GABA A neurotransmitters are ionotropic, meaning they directly affect ion channels, and they act quickly to open chloride channels. They have a tau rise of about 1 millisecond, so a sharp drop down. And then they have a tau fall of 6 milliseconds, which is still reasonably fast, so the return to zero is again pretty quick. GABA B, on the other hand, is a metabotropic, or binds to metabotropic receptors, and that acts slowly via second messengers that open potassium channels. And this has a tau rise of around 25 to 50 milliseconds, which means it slowly becomes open, increasing the current leaving the cell. And then it has a tau fall of 100 to 300 milliseconds, which means that it takes a very long time for this to return back to the resting state. And there's glutamate, and glutamate covers several receptor types, and the receptor types are named for the artificial drugs that selectively bind to them, the agonists for these receptors. But glutamate is a natural neurotransmitter, and it binds to all these receptors. So for AMPA receptors, as we've talked about, it activates sodium and potassium ion channels for a very fast response to a presynaptic spike, and it is modeled again by a single exponential with a fall time of 2 to 5 milliseconds, right? So we just do the constant delta increase instead of having the exponential curve up, and we just drop off really, really quickly. For NMDA receptors, glutamate activates sodium, potassium, and calcium ions, and this has a moderate rise time of 3 to 15 milliseconds, so it's a little bit slower, getting to the peak, and then a fall time of 40 to 100 milliseconds. The NMDA synapse is also an interesting one, so let's look at that in a little more detail. So again, as previously mentioned, NMDA can activate sodium, potassium, and calcium ion channels. It is activated not only by neurotransmitters, but also by voltage. And you see, so NMDA has a magnesium ion that is that blocks this channel. So glutamate comes into the synaptic cleft. It activates both the NMDA receptor and the AMPA receptor. And what happens then is the AMPA receptor is activated, sodium goes in, it depolarizes the cell, and then at a certain point, about minus 50 millivolts, which is somewhere around the spiking threshold, this magnesium ion stops blocking the channel. And then, given that glutamate has already bound to this channel, calcium ions now start, and that's a 2+ ion, start flowing into the neuron. And so what's interesting, though, is that calcium ions also play a role in long-term synaptic plasticity and learning. And because glutamate, which is a presynaptic component, and the postsynaptic membrane voltage are both required to open an NMDA channel, they can act as coincidence detectors, right? So you need a presynaptic spike for glutamate to come out at all, and then you need a postsynaptic spike, more or less, to open the NMDA receptor. That means that the pre and postsynaptic spikes have happened very close together in time. So this could be a possible mechanism for Hebbian learning. And if you remember way back from when we were talking about unsupervised learning, we covered Hebb's rule. The adage was neurons that fire together wire together. And so here we have something that looks like it fits the bill for a temporal coincidence detector, and something that will activate when a presynaptic spike and a postsynaptic spike occur close together in time. So let's explore then how we can implement some kind of short-term plasticity in our synapse model using our model of conductance. In our artificial neural networks, we implemented learning by changing the synaptic weights. In the context of biological neural networks, we would call this kind of learning long-term plasticity. Here we are changing the conductance for synaptic channels, and where in our learning algorithm for ANNs we made changes based on prediction errors or whatever our unsupervised learning rules were if we were doing unsupervised learning. Now we are creating changes in conductance based on just the recent history of what's been going on at the synapse. Now, some of these synapses will increase their conductance if they've been active recently. This would say we would say these have been facilitated. And then other synapses will decrease their conductance if they've been, decrease their conductance rather, if they've been activated recently. And this is called depression. Together, this is referred to as short-term plasticity, which is distinct from learning weight changes, which would be the long-term plasticity. And so we should note that that not only, this is not the only, sorry, we should note that this kind of learning through conductance changes is not the only form of learning that happens in the brain. There is, as we said, there's long-term potentiation, which is like changing the synaptic weight. There is, we can have changes in dendritic spines, which are little protrusions from the synapse. Actually, these right here are dendritic spines. So this is the dendrite that connects up to the main neuron body. The dendritic spine protrudes out, and then the synapse can be formed between the presynaptic neuron and this point on the dendritic spine. So we can have more spines growing. We could create new synapses. There are other ways that learning happens, and we are not discussing those here right now. We are just discussing short-term plasticity induced by changes in conductance at the synapse. So let's model this. And we talked about before, we were assuming that the activation, the state, the probability of transmitter release at the presynaptic neuron was constant. And so now we're going to relax that assumption, and we're going to allow this value to change. And this is how we're going to encode this kind of short-term plasticity. So we will not specify the exact biological mechanism for this change in activity. It could be related to the vesicles becoming exhausted in the case of depression, or transmitter accumulating in the cleft, or any other of a number of reasons. But what we will define here is the dynamics of the probability of transmitter release, this P pre of T. And we will define it to be an exponential decay from whatever the current value of the probability of release is as it decays back to some resting value P0. And this is again controlled by some time constant tau pre. Whenever the synaptic neuron spikes, that conductance, however, will then be incremented by, or rather we should say the probability of release is incremented by some value, and that in turn affects the conductance. And that number will be, whatever that constant number is here, we have delta P of D for depression, delta P of F for facilitation. That will be multiplied by a function of the probability of release. So in the case of depression, the change in the probability of release has added to it a negative number, delta PD, because this quantity needs to be negative because we're reducing the probability of release, and that is multiplied by the probability of the current probability of release. The purpose, and then if it's facilitating, then we add a positive number times 1 minus the probability of release. And the reason behind using these two probabilities here is just to make sure that this probability of release never leaves the range of values between 0 and 1. And so what we see here on these graphs, the red box on the left is the result of depression, the blue box on the right is the result of facilitation, and we see this sort of jagged curve, which is the result, or this shows the change in membrane potential while a train of spikes is being fed through a synapse. And so what you can see is that in the case of depression, after each spike, the change in potential is less and less and less and less, and it tends to decay down to nothing. And in the case of facilitation, the change in potential increases, generally speaking, up onto the top. And again, once the spike train stops, the membrane potential then decays back to the resting state. And what's happening here is, in the case of depression, the probability of transmitter release is decreasing, which reduces the conductance, which allows less current to travel through the synapse, which reduces the total change in membrane potential that can happen in the neuron. And the reverse here is happening in the case of facilitation. The probability of release is increasing, which in turn increases the conductance of the synapse, which lets more current through, which increases the change in potential as the spikes are incident on the neuron. So that concludes our discussion of the synapse conductance models. Like the Hodgkin-Huxley model, we described a current in terms of a channel with a variable conductance. And this time, unlike the Hodgkin-Huxley model, our conductance depends on activity both in the pre- and postsynaptic neurons. Although our preliminary model, we were able to replicate results of neurotransmitter-induced conductance changes by only modeling dynamics of the postsynaptic neuron. When we expanded our model to include dynamics of the presynaptic neuron, this allowed us to build a model of short-term plasticity. As with neuron models, we can make these models, again, arbitrarily more complex, and the kind of modeling you do really depends on the objective of your work. So we're going to leave synapses for now, and in the next video, I should say, we're going to be moving on into increasing the complexity of our neuron model by giving our neuron the concept of spatial extent. See you then.